Welcome. In this video, I'm going to demonstrate how to find the volume of a solid of rotation using the cylindrical shells method. Here we're given a region bounded by x equals y squared and y equals 3 in the first quadrant, and we're rotating about the x-axis. So let's begin with a sketch. Okay, so this is what we're working with. In purple, I have the parabola x equals y squared, and in blue is the line y equals 3. And we want the region in the first quadrant, so that would be this whole section here. Now, as always, it would help to see what this looks like in 3 dimensions when it is rotated about the x-axis. The x-axis is in red, the y-axis is in green, and as you can see here, the whole surface, our region is being rotated about the red x-axis. So here is our two-dimensional hand-drawn sketch of our region, which is here. And here is the three-dimensional rendering of the solid whose volume we are trying to find. Okay, so let's review in the most basic terms what it means to find a volume by cylindrical shells. The integral of the circumference of the cylinder, multiply that by the height, and multiply that by the width. All right, so now that we have this very informal integral for computing the volume of this solid or any solid of revolution using cylindrical shells, let's start figuring out what the different parts are. So suppose this is my cylindrical shell, and that is this distance here, and it's parallel to the y-axis, so it's the change in these y values, so it's delta y. Okay, so I can replace that with delta y. What is the height? Well, the height starts here at the y-axis and ends at this purple line. And this purple line is just equal to y squared. All right, so that's my height. And now what's the circumference? Well, the circumference of this circular base is just 2 pi r. And I'm going to leave that r blank so we can figure out what the radius actually is. Well, for this cylinder, its center is here at the x-axis, and its radius goes all the way up here to y. So the radius is just y. So this integral here nearly represents the volume of this solid. We're just missing our limits of integration. And as we can see here, y runs from a minimum of 0 to a max of 3. So this volume is given by 2 pi times the integral from 0 to 3 of y cubed dy. This integrates to 2 pi times y to the 4th over 4, and we needed to evaluate now from 0 to 3. And we're left with just 81 pi over 2. I hope this video was helpful.